Hello again. This video is primarily about Newton's three laws, which are laws about force and acceleration and how objects move. And before we get into it, I want to spend a little bit of time just talking about what physics looked like before Newton wrote his laws, because it was pretty different, and you might find this a little bit interesting. If just sit back, don't take notes on this because most of this is old ideas that are definitely incorrect, but we'll use it to set up what's going to come in a minute. So, the ideas of physics before Newton had to do with something that they called natural place. And they said that the world is made up of five spheres. And the biggest one on the outside was the sphere of ether, which was where the planets and the stars lived. And inside that, lower than that, there was, oops, sorry, there was the sphere of fire. I believe comets belong to the sphere of fire. Below that was the atmosphere, what they called the sphere of air. Inside the sphere of air was the sphere of water. And at the very bottom, the lowest, was the sphere of earth, where we live. And the point of all this was that every material had its natural place, and that was with other things from its sphere. So if you take a rock and you drop it into water, the rock will go, well, I'm out of place here. I should be in the sphere of earth because I'm made of earth. Therefore, I should sink down. I will sink down through this water and keep sinking until I get to the seabed. And now that I'm back in the sphere of earth, I will come to rest there. If you have bubbles underwater, they will say, well, I'm made of air. Therefore, I should be up in the sphere of air. I should rise up. And I'll keep rising until I get back to the sphere of air. Then I can stop. And both of those things really do happen, so that wasn't completely ridiculous. If you lit a fire, the fire would float upwards through the air, and I mean, they couldn't see where fire ended up, and so what they figured happened was the fire keeps rising through the air until it makes its way back to the sphere of fire, and then it comes to rest. The stars and the planets and the gods were supposed to be made of this top thing, which was called the fifth element. You hear that term sometimes. And if you ever hear the word quintessence, quint means five, essence means element. So that's another word that means the fifth thing, something that's extraordinary and not part of everyday life. They figured that if anything divine or anything from the sky ever ended up on Earth, it would very quickly rise up through the water and air and fire and try to make its way back to its original place. And if you are standing on the surface of the Earth and you throw a rock upwards, they didn't really talk about gravity. They talked about you are taking this rock out of its natural place up into the sphere of air is probably where you throw it. And then the rock says, wait, I'm made of earth. I should be down in the sphere of earth. I shall fall until I get back to the sphere of earth, and then I shall stop. So that explained a fair number of everyday occurrences. And when Newton started writing his laws, one of the things he had to do was knock down this old system before he could start explaining anything new. And so his very first law was about contradicting this natural place idea. So let's get into what he said, and you can kind of see from the wording if you read what he wrote that he was interested in knocking down this old system because he had new ideas that didn't fit with it. I don't think I'll be able to shrink that. We'll just have to get rid of it. All right, so I don't have what he wrote exactly memorized, so I'm going to give you my best approximation of it, and then we'll talk about what it actually means. Newton's first law: any object in motion will remain in motion unless acted upon by an external Either unbalanced or unbalancing, you hear them both. Force. So, what does that mean? The original idea was that objects want to get to a particular place, and once they get there, they will stop. And that was the first thing that Newton wanted to dispense with. The new idea was, once an object is moving, it will keep moving, and it will keep moving forever until something acts to stop it. Objects do not have a natural place. And you've seen objects floating in space, and you know that in space, or most of us have seen this anyway, if you throw something in space, it will fly in a straight line essentially forever until it either runs into something or gets within the gravitational influence of some object that makes it change direction. It will keep moving at the same speed, in the same direction, pretty much indefinitely. Objects in motion just remain in motion. If you want something to change its motion, the only way to do it is to put a force on it. You must pull on it or push on it somehow, either by touching it, or by exerting gravity on it, or by getting a magnet close to it. You have to do something to change its direction. So, we almost never use this when we're doing physics calculations, and you may kind of forget about this one because it doesn't have a lot of practical application. But it was a big deal at the time because this completely struck down the idea of natural position. Objects don't have a place that they want to get to. They just go in whatever direction they're moving, or if they're sitting still, they continue sitting still, and the only way to get them moving is not to tell them that they're out of their natural place, there's no such thing, but to either give them a pull or a push, what we call an unbalanced force. Fair enough. We'll talk a lot later, by the way, about how to analyze forces and determine what are external forces and what are unbalanced forces. For now, don't worry a tremendous amount about those two words. You could just as well say Newton's law as an object in motion will remain in motion unless acted upon by a force. That's pretty close to that's the most important idea in there. All right. His second law, I'm going to write it in English, but that's not the way it's normally formulated, and we'll get to that very quickly. The acceleration of an object is proportional to the force exerted upon it and inversely proportional to its mass. That's how he said it. If you write that mathematically, it looks like this. The acceleration of an object is proportional to the force you put on it, and inversely proportional, meaning divided by its mass. And technically this acceleration and this force should have little vector arrows on them. So A equals F over M. Now, even though this is the way it was originally presented, most people multiply both sides of this by M. That cancels. And they write, this is the much more famous form that most people think of as Newton's second law, F equals ma, which says, if you want to get an object moving, the force that will be required equals how massive is the object times how fast do you want it to accelerate. So his first law says, if you want something to move, you'll need to put some force on it. The second law says, speaking of force, if you know how much force you've got, you can determine how much the object will accelerate, and from there you can figure out, using kinematics, what will its final velocity be, how long will it take to get somewhere. All of our kinematics formulae tie into this. As soon as you have an acceleration, you can start doing kinematics. So, plenty of application for that. And there was a third one. Newton's third law is probably the one that most people have heard of. It's the for every action there's an equal and opposite reaction. Except when he wrote it, he wasn't talking generally about actions, he was talking about forces. And so his version was for every action, force, there is an equal and opposite reaction force. These days people use this for things like if you threaten to raise taxes, you will lose the next election, and they say that's like an action and reaction. That's not at all what Newton was talking about. His version was simply, well, it's something like this. Here's a big rock. And here's a person. Is it fair to say, unnaturally long arm, that if this person touches the rock, then the rock is touching the person at the same time? Does that sound reasonable? I think that's true. If touching is a two-way street, where if you're touching something, it's touching you as well. And with forces, it works the same way. If you push on a rock, if you exert 10 newtons of force with your hand against the rock, your hand is going to feel a 10 newton push in the exact opposite direction, pushing back at you. The force you put on the rock is usually what we call the action, and the pushback force that you feel is a reaction force. And the fact that these cancel out, that doesn't mean the rock can't move, but what it means is your hand isn't going to sink into the rock. Your hand's pushing into the rock pushes back equally hard, and so your hand and the rock don't fuse together. You could get pushed back by this force. If you're a light person, you might rock backwards because you pushed off the rock, or the rock might get moving, or maybe both. The rock might take off this way while you get pushed back the opposite direction, but both of you feel a force when you push on each other. Similarly, if this is the ground and this is you, if you weigh 150 pounds, that means your feet put 150 pounds of force down into the ground, and the ground pushes up on your feet also with 150 pounds of force. And that's why you don't sink into the ground. Now, if you're standing on snow or mud or something, maybe this force is less than 150 and you will sink into the ground, but typically for rigid objects, you push on them and they push exactly as hard back at you in exactly the opposite direction. And we're going to use that when we're setting up free body diagrams, and this mostly explains why people don't sink into the ground and hands don't sink into rocks. When you generate a force, there's another force that compensates for you, that pushes back in the opposite direction, or that pulls in the opposite direction. One more example. If this is the ceiling, and there's a rope attached to this, and you come up and you pull on the rope. If you pull down on the rope with 60 newtons of force, you'll feel an upward pull on your hand that's also 60 newtons. This is why people can climb ropes, because when you pull down on a rope, it lifts up on you with an equal and opposite amount of force. So we'll use that later when we're analyzing forces. There's plenty more to say about how to do the math on this and what forces apply to an object, but for now, just wanted to get down Newton's 3 laws so that you've seen them all in one place. So the first one is object in motion will remain in motion unless you put a force on it. The second one is just F equals ma. And the third one is when you push on something, it pushes back, or if you pull on something, it pulls back.